You've joined us for another deep dive, and today, well, hold on to your hats, because we're about to explore a perspective that turns everything we thought we knew about our place in the cosmos completely upside down. We're plunging into the arguments against the Earth's rotation. Now, I can practically hear the record scratch in your mind, right? It sounds wild, I know.
It does. It really does seem to fly in the face of, well, everything we've been taught, doesn't it?
Yeah.
The idea that the ground beneath our feet might not be constantly whizzing eastward at, hundreds of miles an hour. It's definitely a head-scratcher for most of us raised on the Copernican model.
Totally.
We're setting out on an intellectual adventure, really, to explore the fascinating arguments put forward by those who believe the Earth remains stationary.
Exactly. Think of us as your guides through some pretty unconventional intellectual terrain today. We've gathered a really intriguing collection of sources for this.
We have. And that's how we do it here. So hit that like and the notification bell so that the algorithm won't manipulate what kind of information you can or can't be exposed to. It's how we can tell big tech, hey, I am the master of my own thoughts. You big tech, you can just host the video. Yep, we're going there. Okay, so Earth stands fast. It's championing what's called the Tychonian system.
Right.
Could you break that down for us? What's the basic picture this system paints?
So at its heart, the Tychonian system puts the Earth front and center. Stationary, no spinning, no orbiting.
Solid as a rock.
Exactly. Now, the sun, instead of having us going around it, actually revolves around the Earth.
Okay, that's a big switch.
It is. But here's where it gets interesting. The other planets, Mercury, Venus, Mars, the whole gang, they're all orbiting the sun.
Got it.
So it's kind of a hybrid, right? Keeps Earth central, but also incorporates that heliocentric arrangement for the planets relative to the sun.
Right, makes sense.
And that helped explain some of the more detailed observations they were making.
And it's crucial to remember, this Tycho Brahe guy, he was messing around. He was a top-tier astronomer.
Absolutely no backyard telescope for this guy.
Yeah, he had the resources to get the best instruments, wasn't just making stuff up.
His system was built on incredibly precise data.
Okay, so picture this. Earth stands fast, takes aim at the idea of a spinning Earth. And one of the first things they bring up is the Foucault pendulum.
That's usually presented as pretty solid proof that the Earth is rotating.
What's their counter-argument? What did they think was happening with that pendulum?
Well, they make some interesting points. First, they observed that the pendulum doesn't just swing until it lines up with a single parallel circle on the ground and then stop.
Right.
If the Earth turning underneath it were the only thing going on, it theoretically should stop deviating at that point.
Makes sense.
But they observed it keeps deviating. And then, this is a big one, they claim that the speed of the deviation actually changes depending on the weight of the pendulum bob. Heavier bob, slower deviation. Lighter bob, faster deviation.
Interesting.
So they're saying if Earth's rotation were the only factor, it should affect all pendulums the same way, regardless of their weight. The key takeaway, as they saw it, was that there had to be something else going on, some other force influencing the pendulum.
Some mystery force.
Right. They say something unknown to us.
Yeah.
So they weren't necessarily denying what they were seeing, just questioning the common interpretation.
Got it. Now, another big argument against a stationary Earth.
Yeah.
The sheer speed, the sun, moon, and stars would have to be traveling to circle us every day.
Right.
It seems ridiculous. How does Earth Stands Fast address that?
Well, they admit it's a powerful argument that at one time those speeds seemed almost impossible to imagine, but they argue that with the advancements in science, especially understanding the crazy speeds of light and electricity, that objection doesn't hold as much weight anymore.
They're basically saying, hey, we know more about speed now.
Exactly. They even use this analogy of someone from the countryside never having seen a train trying to grasp how fast it moves.
So our idea of what's possible can change as our knowledge expands.
Right. Just because we don't experience those kinds of speeds every day doesn't mean they can't exist.
Makes sense. Let's move on to the Earth's equatorial bulge.
Okay.
We're taught that's caused by the centrifugal force of Earth's spin. How does Earth Stands Fast? Explain it.
They offer two interesting alternatives. First, they say that over, thousands and thousands of years, the heat in the tropics has slowly caused the equatorial regions to expand.
Interesting.
And at the same time, the cold at the poles is causing a constant contraction.
So it's like a gradual reshaping due to temperature differences.
Right. Their second explanation is that the Earth is actually growing.
Growing.
Yeah, they say the accumulation of plants, animals, geological stuff like coal, it all adds up to more mass at the equator.
Huh. So instead of a force from spinning, it's about slow processes over huge timescales and the addition of matter.
Exactly.
That's fascinating. So let's talk about something a bit more specific. Richter's observation of pendulum clocks. He found they run differently at the equator versus on mountains.
Right. The classic explanation is that gravity changes due to centrifugal force from Earth's spin.
What's the Tychonian take on that?
Well, they turn that whole idea on its head.
How so?
They say the reason the pendulum slows down at the equator isn't because gravity is weaker there. It's because gravity is actually stronger.
Stronger? How?
Because of that extra mass at the equator, remember? They say that adds to the weight of the pendulum bob, slowing it down.
So instead of a decrease in gravity from spinning, it's an increase in gravity from more mass.
Exactly. And on mountains, the pendulum speeds up because there's less mass around, so a weaker pull.
It's a complete reversal of how we usually think about it.
Right. They also point out that a pendulum's speed isn't just determined by its length, suggesting other factors are involved.
Okay, so now let's talk about something that seems tough to reconcile with a spinning Earth. The atmosphere. How do these sources argue against the idea of the atmosphere just sticking to a rotating Earth?
The author really struggles with this one.
Yeah.
They say it's just so hard to understand how the air, which is so light and constantly moving around, wouldn't be massively affected by the Earth spinning.
Right. It's not like it's glued to the ground.
Exactly. They argue that if the Earth were spinning eastward at hundreds of miles per hour, there would have to be this constant, powerful westward air current.
Like the air getting left behind as the Earth zooms underneath it.
Right. And they even calculate that it would be way stronger than any hurricane we've ever seen.
So where's that massive, constant westward hurricane?
That's their point. Now, the standard explanation is that the atmosphere gets dragged along by Earth's rotation.
Through something called communicated motion, right?
Yeah, but they argue that only really applies to solid, connected objects, not to air, which is just a bunch of loosely connected gas molecules.
So the air wouldn't just politely follow along.
Especially not the thinner air higher up.
Okay, now I remember they also bring up this concept of ether.
Right, which was a popular idea back then.
Yeah, like a medium for light to travel through.
Exactly. They suggest that this ether would actually resist the Earth's movement, causing the outer layers of air to lag behind and push on the lower layers.
Okay, and that would create
an eastward flow of the whole air belt.
Interesting.
But even without the ether idea, they still maintain that the lack of these insane westward winds is a major problem for a rotating Earth.
Yeah, it just makes intuitive sense. If the ground's moving that fast, why isn't the air constantly trying to catch up?
Right. It really makes you question how the atmosphere is supposed to stay in sync with a spinning planet.
Now, what about gravity? They bring up the argument that if the Earth is orbiting the sun, gravity should always be pointing towards the sun.
Right. They use this analogy of dust sticking to a wall where gravity's pulling it towards the wall. They say the same should apply to Earth and the sun. If the sun's gravity is keeping Earth in orbit, then Earth's gravity, what pulls us down, should always be pointing towards the sun.
But it's not, right?
No. We always feel gravity pulling us towards the center of the Earth no matter where the sun is in the sky.
So that's a pretty big problem for the idea that Earth is orbiting the sun under its gravitational control.
Exactly.
Okay, now, what about day and night and the seasons? How does the Tychonian system explain those?
For day and night, it's straightforward. The sun just circles the Earth every 24 hours.
Simple as that.
Right. For the seasons, they actually refer to the standard explanation with Earth tilted on its axis as it goes around the sun.
Okay.
But then they point out something they find confusing. The idea that Earth is spinning while it's also orbiting.
Right.
They argue that if the sun's gravity is strong enough to keep Earth in orbit, it should have also locked Earth into a single orientation facing the sun.
Like how the moon always shows us the same face.
Exactly.
That would mean one side of Earth always in daylight, the other always in darkness.
Right, which is obviously not what we see.
So they're saying spinning and orbiting at the same time under those gravitational rules just doesn't work.
It seems like a contradiction within the model itself.
Yeah, it's a good point. Now, you mentioned that they draw a parallel between Earth always facing the sun and the idea from Newtonian physics that the Earth and sun should always be showing each other the same faces.
Yes, they point to that expected outcome of Newtonian gravity as further evidence against Earth's rotation.
Explain that a little more.
So they're saying that if gravity really wants to lock things into facing each other, like the Earth and the Moon have done over time, then the idea of Earth spinning while orbiting the sun becomes even more problematic.
Because it should have stopped spinning by now.
Exactly. It creates a fundamental inconsistency within the Copernican model.
Okay, so they see this tidal locking thing as a major problem for the idea of a spinning, orbiting Earth. Now, they also paint this vivid picture of Earth's atmosphere trailing behind us like a comet's tail if we were moving around the sun.
Oh, yes. They really lean into that analogy.
What do they say exactly?
They argue that if Earth were zooming through space, the air, because it's not solidly attached, would naturally lag behind.
Like getting left behind.
Yeah, and they say it would stretch out like a long tail, just like how we see comets with their tails pointing away from the sun.
Wow, that's a striking image.
It is, and they point out that we don't see this giant air tail streaming behind Earth, so how could we possibly be moving that fast?
Okay, so it's another argument based on what we don't observe.
Right. The absence of this obvious atmospheric effect is their evidence against Earth's motion.
Now, they also revisit the issue of gravity and say that the forces involved just wouldn't allow Earth to both rotate and revolve around the sun, as described by Copernicus and Newton.
Right. They return to that point about the direction of gravity constantly changing if Earth were orbiting the sun. But they also focus on the sheer strength of gravity that would be needed to keep Earth in its huge orbit.
Okay.
And they argue that a force that powerful would have long ago pulled our atmosphere away from Earth completely.
Like ripped it right off.
Yeah, towards the sun.
Wow.
They compare it to how Earth's gravity is thought to have taken away any substantial atmosphere the moon might have had.
So the fact that we still have air is a problem for the standard model.
According to them, yes. They say either we'd lose our atmosphere or Earth would stop spinning under those gravitational rules.
Okay, so they're saying the Copernican system can't explain why we have both a spinning Earth and an atmosphere.
Right. It's either one or the other.
Now, after laying out all these challenges to the Earth moving, they shift gears and talk about the revolutions in astronomy that would come with accepting a stationary Earth.
They basically lay out what would need to change in our understanding of the cosmos.
Okay, what are some of those big shifts?
The most fundamental one is simply taking all the apparent movements we see in the sky at face value.
So no more saying those are just illusions caused by our motion.
Exactly. Everything is moving as it appears.
Okay.
And that means a huge change in how we think about stars and planets.
How so?
Well, they say we'd have to abandon the idea that stars are distant suns like our own.
Interesting.
And we'd have to rethink the idea that planets are Earth-like places. Because all our calculations about mass, size, distance, all that stuff is based on the sun being this big, dominant star at the center. If Earth is the center instead, those calculations are all wrong.
So it would require a complete reevaluation of how we understand everything out there.
Exactly. They also say we don't fully understand how visual angles work over those immense distances.
And they even challenge calculations based on lunar eclipses.
Questioning whether the laws of refraction, how light bends that we see on Earth, apply accurately to the space between Earth and the moon.
So they're essentially saying we can't be sure our current methods are giving us the right answers.
And they go even further, using the simple act of seeing a light from a distance to challenge the whole idea of stars being incredibly far away.
Yeah.
Well, think about it. You can see a small candle flame from pretty far away, farther than its size would suggest if you just scaled things up proportionally.
Right.
They say maybe the stars aren't as huge and distant as we think, and their small size in the sky is just due to a combination of their actual size and our atmosphere making them look smaller.
So our understanding of the universe might be way off if we're misjudging those distances.
Exactly. They also point out that things look clearer and bigger on very cold, clear nights.
Right, when the air is really crisp.
Exactly. They say that shows how much our atmosphere affects what we see, and maybe we're not accounting for that enough in our astronomical calculations.
Okay, so what does all this mean for the idea of other planets having atmospheres and whether they could be habitable?
Well, they're pretty skeptical.
In what way?
They basically say it's unlikely other planets have atmospheres like ours.
Why?
Their argument is that if a planet is flying through space at the speeds the Copernican model requires, it wouldn't be able to hold on to its atmosphere for very long.
Like it would just get blown away.
Right. And they point to the moon as an example, which we think has almost no atmosphere.
Okay, so let's move on to some of the further evidence they present for a stationary Earth.
Okay.
They start by talking about the shapes of the continents. What's their argument there?
They point out that the continents are mostly longer north to south than east to west.
Right, most of them kind of stretch from pole to pole.
And they say that contradicts the idea of a strong east-west rotational force shaping the Earth.
How so?
Their logic is that if the Earth were spinning fast, we'd expect to see continents stretched out east to west, perpendicular to that spin.
Because of the centrifugal force.
Right. Instead, they suggest the north-south alignment of the continents points to the influence of the Earth's magnetic poles.
Interesting.
They say the north ends of continents are pulled by the north magnetic pole, and the south ends are pushed by the south magnetic pole over long periods.
So the continents are shaped more by magnetism than rotation.
That's their argument.
Fascinating. And they also mention west winds, right?
Yes, they bring up the work of this guy, Wilhelm Malman, who found that there are prevailing west winds in the temperate latitudes.
Okay.
And they say, if Earth were spinning eastward, we should expect east winds, not west winds.
So another point against Earth's rotation based on what we observe here on the ground.
Right. Now, let's shift our focus entirely and dive into geocentric scientific arguments that have been put forth against the Earth's rotation. This is where things get really interesting from a physics perspective.
Indeed. This is where we get into forces and frames of reference. One of the foundational challenges to the idea of a rotating Earth comes from the work of the physicist and philosopher Ernst Mach.
Mach, yeah. Heard the name. Mach's speed.
Same guy. Yeah, though this is about inertia. He critically examined Newton's laws of motion and questioned the origin of inertial forces like centrifugal force, that outward push you feel when you're on a merry-go-round.
Sure.
Newton argued that these forces were evidence of absolute rotation relative to absolute space itself. But Mach proposed a different idea, a really radical one at the time.
Which was?
He suggested that these inertial forces might actually arise from the gravitational interaction of an object with all the distant masses in the universe. The stars, the galaxies, everything.
Whoa, so the whole universe defines inertia.
In essence, yes. The universe itself, in its entirety, could be the frame of reference that determines inertia, not some abstract, absolute space. That's Mach's principle, basically.
So if Mach's idea is correct, does that mean the experience of centrifugal force on, say, a spinning playground ride doesn't necessarily prove that the Earth itself is rotating?
Exactly right. If inertia is determined by the overall distribution and motion of mass in the universe, then the local experience of centrifugal force doesn't automatically tell us whether the Earth is spinning locally or whether the rest of the universe is rotating around a stationary Earth. Both could potentially produce the same effect locally.
Mind-blowing.
And building on Mach's ideas, another physicist, Turing, did the math. He demonstrated mathematically that within a geocentric framework specifically, a universe rotating around a non-rotating Earth, the centrifugal and Coriolis forces.
Coriolis, yeah, the thing that makes hurricanes spin and stuff.
That's the one. Those forces that seem to deflect moving objects on a rotating Earth, like winds and ocean currents. Turing showed they are not fictitious forces, as they're often called in Newtonian physics when you're in a rotating frame.
Okay, what are they then?
Instead, they arise as real gravitational effects due to the motion of all those distant masses of the universe relative to the stationary Earth.
So they're actual pulls and pushes from the stars.
To put it simply, yes. In a geocentric model informed by Mach's principle, these forces are genuine gravitational interactions caused by the rotating cosmos, not just artifacts of our rotating perspective.
That's a profound shift in perspective, seriously. So those classic proofs of Earth's rotation that we all learned about in school, things like the way Foucault pendulum swings, or the bulge at the Earth's equator, even the behavior of geostationary satellites, are they not definitive proof after all then?
Well, that's precisely the argument. If these phenomena can be equally, and perhaps from their perspective, even more elegantly explained by a geocentric analysis, where these sources are real gravitational consequences of a rotating universe around a stationary Earth.
Then they don't prove Earth rotates.
Exactly. They don't exclusively validate a rotating Earth. Some proponents even argue that a geocentric model that can account for these observations without invoking these fictitious forces might actually be considered a more fundamental, perhaps even simpler, explanation of the universe's mechanics.
Wow. It's a really challenging idea to wrap your head around because we're so ingrained with the standard explanation.
It absolutely is. So the key insight here is that what we typically see as clear evidence for Earth's rotation might just have alternative explanations within a radically different but potentially consistent framework of physics.
This really does make you rethink some basic assumptions. Okay, now let's talk about a concept that's central to many geocentric cosmologies, but largely absent from modern mainstream science: the firmament. What exactly is this in the context of a non-rotating Earth?
In this view, it isn't just a metaphorical or poetic term you find in ancient texts like Genesis.
No.
No, it's understood as a real, physical, and incredibly massive structure created on the second day of creation.
A physical structure? Like what?
Well, its exact nature is debated among proponents. Some have proposed it to be a solid dome, maybe metallic or crystalline, while others have envisioned it more as a vast expanse, maybe containing layers or even water above it.
Okay.
However, the key role of the firmament, regardless of its exact composition, is that it acts as the boundary of our created universe. And crucially, it's the structure within which the stars, the sun, and the moon are embedded or fixed.
So they're attached to it.
Essentially, yes. And this firmament is what carries them around the stationary Earth. It fundamentally governs the mechanics and physics of the cosmos in this model. It sets the stage.
So if the Earth isn't rotating, what role does this rotating firmament play in explaining the day-night cycle and the movement of all the celestial bodies we see?
The firmament in this model is in constant rotation around the stationary Earth, completing one full rotation approximately every 24 hours.
Ah, okay. So it's spinning, not us.
Precisely. This rotation is what carries the sun, the moon, and all the stars across the sky from east to west, creating our day-night cycle and the apparent movement of the constellations.
Makes sense within that model.
Furthermore, the firmament is often considered to be the fundamental frame of reference for light itself.
For light, how does that work?
Well, the speed of light, in this view, isn't necessarily a universal constant in empty space in the way Einstein described it in special relativity. Instead, it's a speed defined relative to this rotating firmament.
C, relative to the firmament.
Okay. So it's the motion of the firmament that dictates the apparent movement of everything we see in the heavens and potentially affects how light propagates. And some proponents are actually actively exploring potential experimental ways to detect some kind of dependence of physical laws on the properties and rotation of this hypothetical firmament.
Wow, trying to find evidence for it today.
Yeah. The core idea here is that the firmament's rotation is the engine that drives the celestial mechanics in a non-rotating Earth cosmology.
That's a truly grand and almost, I don't know, Tolkien-esque vision of the universe. Like something out of myth, but proposed scientifically.
It has that quality, doesn't it?
It does. Now, how are phenomena like the change of seasons and the seemingly backward or retrograde motion of some planets explained within this firmament-centered geocentric model? Those seem tricky.
They require a bit more geometric complexity, it's true. Seasons in this framework are explained not by the Earth's axial tilt in its orbit around the sun.
Which is the standard explanation.
Right. Instead, they're explained by the sun's own yearly journey, as it's carried by the rotating firmament. Imagine the sun following a slightly spiraling path as it moves around the Earth each day with the firmament.
A spiral.
Yeah. Over the course of a year, this spiral motion takes the sun further north relative to the Earth's equator during our summer, resulting in longer days and more direct sunlight for the northern hemisphere.
And further south in winter.
Exactly. Leading to shorter days and less direct sunlight. The equinoxes mark the points where the sun's path crosses the celestial equator.
Okay, that accounts for seasons. What about that weird retrograde motion of planets like Mars, where they seem to loop backwards in the sky sometimes?
Ah, retrograde motion. This is explained usually by adopting something similar to the Tychonic system, developed by Tycho Brahe.
Okay, remind me.
In that system, the Earth is stationary, the sun orbits the Earth, but the other planets, Mars, Jupiter, Venus, etc., orbit the sun.
Hybrid model almost.
Kind of. So as the sun carries these orbiting planets around the stationary Earth, the combination of the sun's larger orbit around Earth and the planet's smaller orbits around the sun creates those apparent backward loops from our perspective on Earth.
So it's the geometry of the sun-orbiting planets being carried around the Earth.
Exactly. It's a more complex geometrical arrangement than the simple heliocentric model for planetary motion.
Right.
But it does reproduce the observations. So the key is that these phenomena are accounted for through specific coordinated movements within this geocentric framework, often involving the sun orbiting Earth and planets orbiting the sun.
It's certainly a very different way of picturing the solar system and the universe beyond. And you mentioned earlier that there's a historical connection drawn by some between heliocentrism and pagan philosophy and astrology. Can you elaborate briefly on that?
Yes. Some proponents of geocentrism argue that the roots of the heliocentric idea can be traced back further than Copernicus to ancient Greek philosophies, particularly Pythagorean ideas that maybe emphasized a central fire or a moving earth for sort of philosophical or numerological reasons.
Okay.
They also point to the prominent role of the sun in various ancient pagan religions and in Babylonian astrology. The suggestion is that when Copernicus revived the heliocentric model during the Renaissance, he might have been influenced, consciously or unconsciously, by these pre-Christian ideas, as perhaps were some of his early followers like Kepler, who had mystical leanings.
So a pagan origin argument?
Somewhat, yeah. Furthermore, they sometimes argue that the widespread acceptance of heliocentrism in the 17th century has significant social and theological ramifications, potentially undermining the authority of the Bible as a source of scientific truth, since it seemed to contradict Scripture, and by extension, maybe its authority in other domains as well.
So a challenge to scriptural authority.
That's part of the narrative for some. So, for them, the historical origins and consequences of heliocentrism are intertwined with non-Christian worldviews, or a shift away from biblical authority.
Okay, interesting historical perspective there. Let's move on now to what some interpret as evidence from modern science that might, perhaps surprisingly, support a geocentric view. This is where things can get quite contentious, I imagine.
Absolutely, because it involves interpreting data that most scientists see very differently. One key area that's often cited is the cosmic microwave background radiation, the CMB.
The afterglow of the Big Bang, right?
That's the standard interpretation, yes.
And according to standard cosmology, which is fundamentally built on the Copernican principle, the idea that Earth doesn't occupy any special or privileged position in the universe.
We're just on a random speck of dust.
Basically, yeah. The CMB should be largely uniform, isotropic in all directions, smooth.
But it's not perfectly smooth, is it? No, there are tiny temperature fluctuations. But beyond those, analyses of CMB data from satellites like COBE, WMAP, and Planck have revealed certain larger-scale anomalies, unexpected patterns.
Such as?
Including alignments with the plane of our own solar system, the ecliptic plane, and even with the direction of the Earth's equinoxes. These large features seem strangely aligned with us.
Alignments with Earth? That sounds un-Copernican.
It does seem that way, yes. And those who argue for a geocentric universe interpret these alignments as potentially indicating that the Earth is, in fact, in a central or somehow preferred location in the universe.
If the biggest thing we see is aligned with us, maybe we're special.
That's the implication they draw. They point out that if the largest scale structure we can observe, the CMB, shows this unexpected correlation with Earth-based alignments, it suggests our planet might not be just any random point in the cosmos after all.
Has mainstream science acknowledged these alignments?
Oh yes, the alignments themselves are well documented in the scientific literature, often referred to as the axis of evil, jokingly, because they're so problematic for the standard model. Mainstream explanations usually involve statistical flukes, contamination from foreground sources, or perhaps unknown physics.
But the geocentrists see it differently.
They see it as positive evidence. They also quote cosmologists like George F.R. Ellis, who acknowledged years ago that when analyzing CMB anisotropies, we often assume the Copernican principle from the outset. The analysis doesn't necessarily prove it independently.
So it's baked into the interpretation.
Awesome, yes. So these anomalies are seen by geocentrists as potential cracks in the foundation of the standard cosmological model, hinting at Earth's centrality.
There's also mention of the distribution of quasars, those incredibly luminous distant objects. What's the geocentric angle on that?
Yes, this relates to work by astronomers like Holton Arp, who was known for challenging conventional views, and others like V.M. Varshney. They conducted analyses of the spatial distribution of quasars based on their redshift values.
And what did they find?
They found some evidence suggesting that quasars might not be randomly distributed, but instead might be arranged in spherical shells, or at least concentrated at specific distances, that appear to be centered on the Earth, or at least our region of the galaxy.
Cells of quasars centered on us. Again, very un-Copernican.
Highly un-Copernican, yes. If this pattern were definitively confirmed and couldn't be explained away by selection effects or other biases, it would fundamentally challenge the cosmological principle. That principle states the universe should be homogeneous, basically the same everywhere, and isotropic the same in all directions on large scales.
So finding structure centered on us breaks that principle.
It certainly appears to. Varshney himself proposed other potential explanations for his findings, related to the nature of quasars, But the raw observation of apparent Earth-centered shells is interpreted by some geocentrists as further indication of a preferred Earth-centered frame of reference in the universe.
So CMB alignments, quasar shells. What else? The concept of redshift comes into play here too, doesn't it? The stretching of light from distant galaxies.
Yes, the interpretation of redshift is another major point of divergence. Standard cosmology interprets redshift almost exclusively as a Doppler effect due to recession velocity, plus the stretching of space itself evidence for the expansion of the universe.
Right, Hubble's law. Further away means faster recession means more redshift.
That's the standard picture. However, geocentrists often point out that Edwin Hubble himself, in his early papers, was actually quite cautious about stating definitively that redshift was only a measure of recession velocity. He considered other possibilities.
He wasn't totally sure.
He expressed reservations. And our sources mention physicist Louis Marmé compiled a list of no fewer than 60 different theories proposed over the years to explain the phenomenon of redshift, not all involving simple velocity.
60 different theories. Wow.
Yeah, indicating it might not be as settled as often presented. Researchers like Holt and Arp, whom we mentioned regarding quasars, presented decades of evidence for what he called intrinsic redshifts.
Intrinsic, meaning
That part of an object's redshift might be an inherent property of the object itself, maybe related to its age or composition, and not solely due to its motion away from us or cosmic expansion. He showed examples of high redshift quasars seemingly physically connected to low redshift galaxies.
which shouldn't happen if redshift only means distance and velocity.
Exactly. It challenges the standard interpretation. And then there's the idea of the Copernican embarrassment related to redshift quantization.
Quantization, like steps.
Some studies have suggested that redshifts don't vary smoothly but come in preferred quantized values. If this is true, and we see these equal redshift steps in all directions.
It would imply we're at the center of concentric shells again, like ripples from explosions.
Precisely. It would imply we are at the center of a series of cosmic structures or events, which is a very, very un-Copernican conclusion. So the geocentric view often considers these alternative interpretations and observations regarding redshift as undermining the standard picture of a uniformly expanding, non-centered universe.
So questioning redshift undermines expansion and the Copernican principle.
That's the connection they make, yes. The takeaway is a fundamental questioning of the standard interpretation of redshift as definitive proof of an expanding, non-centered universe.
And that certainly throws a wrench in the standard cosmological narrative we usually hear. Okay, now let's delve into some of the specific experimental evidence that's often interpreted by geocentrists as indicating a motionless Earth. The Michelson-Morley experiment is probably the most famous of these.
It is indeed iconic. Conducted way back in the late 19th century by Albert Michelson and Edward Morley. Its goal was to detect the Earth's motion through a hypothetical medium called the luminiferous ether.
The stuff light was supposed to travel through, like sound through air?
Exactly. They reasoned that if the Earth was moving through this stationary ether, light traveling with the ether wind should go at a different speed than light traveling across it. Their interferometer was designed to detect this tiny difference.
And the result?
Famously, a null result. They detected no significant difference in the speed of light, meaning no detectable motion of the Earth relative to the ether.
Which was a huge shock to physics at the time.
A massive puzzle. It was one of the key experimental results that led Albert Einstein to develop his theory of special relativity, which, crucially, eliminated the need for a stationary ether altogether.
Right. Relativity explains the null result without needing ether.
It does. However, geocentrists look at that original null result and take a different lesson. They see it as straightforward evidence against the Earth's motion through space, or at least against its motion through a detectable ether.
The experiment failed to find motion, therefore there is no motion.
That's the simple interpretation, yes. They also often point out that Einstein himself later, particularly when developing general relativity, seemed to reconsider the concept of an ether, albeit in a modified form linked to space-time itself. So they argue maybe the ether concept wasn't entirely wrong.
Interesting point about Einstein. What about other experiments from that era, like the Fizeau experiment, or Airy's observations of stellar aberration?
Right, there were several others. The Fizeau experiment dealt with the speed of light in moving fluids, like water. Airy's experiment, even earlier, involved filling a telescope with water to see if it affected stellar aberration, that tiny apparent shift in the position of stars caused by the Earth's velocity.
And what did these show, according to the geocentric view?
Well, the interpretations are complex, but geocentrists argue the results of these, along with subsequent ones like experiments by Röntgen, Lodge, the Michelson-Gale experiment, and the Sagnac experiment, produce results that are actually more consistent with either a stationary Earth or a universe that is rotating around a stationary Earth.
Can you give an example?
Sure. The Sagnac experiment, for instance, involves light beams traveling in opposite directions around a rotating platform. It detects a difference in their arrival times that depends on the platform's absolute rotation rate. Geocentrists argue this proves the existence of a preferred frame of reference, an absolute space, relative to which rotation can be measured, a frame in which the Earth can be at rest.
Okay. And Michelson-Gale?
The Michelson-Gale experiment was like a giant Sagnac interferometer laid out on the Earth's surface. It detected a small but measurable fringe shift that corresponded to the Earth's sidereal rotation rate relative to the distant stars. Now, standard physics says this measures Earth's rotation relative to inertial space, but geocentrists can interpret it as measuring the rotation of the cosmos, carrying the ether or space itself around a non-rotating Earth.
So the same result, different interpretation of what's rotating.
Exactly. The key takeaway from all these experiments for geocentrists is that the results are not always seen as unequivocally supporting a moving Earth and rejecting an ether or absolute space. They argue the data can fit their model too, sometimes even better.
The name Dayton Miller keeps coming up in discussions of these ether drift experiments. What was his work, and why is it considered significant in this context?
Dayton Miller. He's a key figure. He was a contemporary of Michelson and Morley and conducted a much more extensive series of ether drift experiments over several decades, from the early 1900s into the 1930s, often at high altitudes like Mount Wilson Observatory.
Using better equipment.
He used a more sensitive interferometer and took meticulous precautions against disturbances. And unlike the largely null results of Michelson-Morley, Miller consistently detected small but, he claimed, statistically significant positive ether drifts.
So he did find evidence of motion relative to an ether.
That's what he concluded, yes. He found a small velocity, varying with direction and time, suggesting the Earth was drifting through an ether, but perhaps the ether near Earth was being partially dragged along with it.
What did mainstream science make of Miller's results?
By and large, mainstream science has generally downplayed or dismissed Miller's findings. Explanations usually involve subtle systematic errors, like temperature effects in his apparatus, or reinterpreting his data within the framework of special relativity, perhaps as fluctuations or noise.
But geocentrists see it differently.
Absolutely. They highlight the sheer volume and meticulousness of Miller's decades of work. They argue that his consistent positive results provide strong evidence for either a stationary Earth within a moving ether, perhaps an ether dragged by the rotation of the universe, or perhaps a truly motionless Earth experiencing effects from a rotating cosmos.
So direct experimental contradiction to the standard narrative.
That's how they present it. They also point to later reanalyses of Miller's data, like one by Robert Shankland, who was actually tasked by Einstein to review Miller's work, which, while ultimately concluded the effects were likely due to temperature, still confirmed the presence of a systematic periodic signal in the data that Miller himself had emphasized.
So even the critiques found something there.
They found the signal Miller reported, yes, though they disagreed on its cause. So Miller's experiments remain a key piece of evidence cited by geocentrists, suggesting the question of ether drift and Earth's motion wasn't as settled as history often portrays it.
Now, one of the most common arguments against geocentrism, maybe the biggest one for many people, is simply complexity. It just seems so much more complicated and contrived to have the entire universe spinning around the Earth compared to the elegant simplicity of the Earth spinning and orbiting the sun. How do geocentrists address this?
That's a fair point. The Occam's razor argument, simpler is better. They address it in a couple of ways. First, they often argue that the underlying geometry, the actual distances between celestial bodies and their relative speeds, are essentially the same in both geocentric models, particularly the Tychonic model we discussed, and heliocentric models.
Tychonic again. Earth still, sun orbits Earth, planets orbit sun.
Right. Mathematically, the descriptions of the relative motions between the planets, sun, and Earth can be made equivalent through simple coordinate transformations. It's just a different choice of what you consider stationary.
So geometrically, it's not necessarily more complex to describe what we see.
Not necessarily, no. The paths might look more complex plotted from an Earth-centered view, but the relative positions and movements are the same. The fundamental difference lies in which body you assign the property of being at rest.
It's about the frame of reference choice.
Exactly. Therefore, they contend that it's not inherently more complex in terms of describing the observed motions themselves. The perceived complexity comes more from the dynamics the forces required.
Ah, the physics needed to make it work.
Yes. And even there, they point to people like Fred Hoyle.
Hoyle, yeah, a prominent astronomer, definitely not a geocentrist.
Not at all. But he famously conceded in some writings that from a purely kinematic standpoint, just describing motion, you could choose any point as the center. He even stated that a geocentric theory is viable observationally.
But he added a caveat, didn't he?
He did. He said it would require more complex laws of physics, particularly regarding the nature of the forces acting on the immensely distant sun and stars to make them orbit the relatively tiny Earth daily in the observed ways. That's the dynamic complexity.
So the forces seem implausible in that model.
From a standard physics perspective, yes. Interestingly, Hoyle also noted something else. If one were to fully account for all the gravitational interactions in such a universe with a truly stationary Earth at the gravitational center, the barycenter, the overall center of mass of the entire universe, would essentially have to coincide with or constantly accelerate towards the Earth. A very peculiar requirement.
Making Earth dynamically special again?
Extremely special, yes.
Okay, finally, let's quickly touch on that connection between Mach's principle, which we discussed earlier, inertia from distant masses, and a concept called perfect dragging within Einstein's theory of general relativity. How might these ideas relate to a non-rotating Earth?
Right, connecting back to Mach.
Yeah.
As a reminder, Mach's principle suggests inertia isn't absolute, but arises from the interaction with all the mass in the universe. Some interpret this as offering potential theoretical support for a geocentric view.
How so?
The idea is that the immense mass of the entire universe rotating daily around a stationary Earth could be what generates the inertial forces, like centrifugal and Coriolis, that we experience locally and attribute to Earth's spin. The rotating universe creates our local inertia.
So the universe's rotation makes things feel like the Earth is spinning.
That's the Machian geocentric idea. Now, frame dragging, sometimes called the lens-Thirring effect, is a prediction of Einstein's general relativity. It says that a rotating mass, like a spinning planet or star, literally drags space-time around with it.
Like stirring honey.
Kind of, yeah. Space-time itself gets twisted. Now, perfect dragging is a more extreme theoretical case. Some theoretical physicists have explored models where if you have a massive rotating shell of matter, representing the universe, surrounding a central object, representing the Earth, it's possible that the interior space-time could be dragged along perfectly with the rotating shell. This means the local inertial frames inside the shell wouldn't rotate relative to the shell itself, but would rotate relative to the distant, non-rotating absolute space outside.
So inside the rotating universe shell, things would behave as if the central Earth was stationary, and the shell's rotation would create the effects we see.
That's the theoretical possibility being explored. If the universe acts as a perfectly dragging, rotating shell, then the local physics inside might be indistinguishable from a situation where the Earth is truly at rest and the universe rotates. It suggests that within the framework of general relativity itself, our most advanced theory of gravity, a form of dynamical geocentrism might not be entirely ruled out, theoretically.
Wow. Highly theoretical, but it keeps the door slightly ajar, maybe.
It's definitely deep in theoretical physics, but it shows the conversation isn't just about old texts. It touches modern physics, too.
Well, this has been an absolutely mind-blowing deep dive, seriously. We've traversed such a vast landscape of arguments against the Earth's rotation.
We really have.
Stretching from those deeply held biblical interpretations that see a stationary Earth as, like, foundational truth.
Based on literal readings.
All the way to these fascinating and, frankly, challenging scientific viewpoints that offer alternative explanations for phenomena we often take as absolute direct proof of our planet's spin and orbit.
And we've explored how these arguments draw upon historical scientific debates, like with Mach and the ether experiments, offer really different reinterpretations of crucial modern experiments and observations like the CMB.
Yeah, the CMB stuff was wild.
And even point to potential anomalies within modern cosmology itself. It's a perspective that undeniably forces us to, at least for a moment, reconsider our fundamental assumptions about the universe and our place within it.
Absolutely. We wanted to open up this fascinating and often completely overlooked corner of intellectual thought to present these arguments as they are understood by those who advocate for them.
Trying to represent them fairly.
And to perhaps leave you, our listener, with maybe a sense of awe at the complexity and the persistent mysteries that still exist in the cosmos. There's still stuff we don't fully get.
For sure. And this kind of exploration, digging into foundational questions, it naturally leads to many more questions than answers, doesn't it?
Oh, absolutely. My head is spinning. Or maybe the universe is spinning around my head. I don't know anymore.
Yeah. We really encourage you to continue your own investigation if this sparked your interest. Delve into the sources we've touched upon and just keep that spirit of intellectual curiosity alive. Question everything.
So as we wrap up this deep dive, here's maybe a provocative thought for you to ponder. If our understanding of something as seemingly fundamental as the Earth's rotation can still be challenged by such a diverse array of arguments spanning millennia, what other scientific paradigms, what other things we take for granted as settled science might actually be ripe for deeper, more critical, more open-minded examination?
It's a humbling thought, isn't it?
Yep.
Makes you realize science is a process, not just a book of final answers.
It really is. And hey, if you found this journey into the counter-arguments against Earth's rotation as thought-provoking and maybe a little bit dizzying as we did,
Hope you did.
be sure to hit that like button and subscribe for more deep dives into the fascinating, the complex, and the often surprising realms of knowledge.
We'll keep digging into interesting stuff.
Until our next exploration.